season switching, now niggas is leaving bitches. Now she is tripping, soon as she began to see the difference. A homegirl called and told her that she seen him slipping.
Okay, so here we're going to minimize the surface area of a cylindrical can of volume 900 centimeters cubed. Okay, so here we have two different equations, and we're going to minimize the surface area. So this is our main equation, the one we're trying to minimize. And then the cylindrical can, okay, and volume will be the other formula. This is going to be one that we'll just utilize as a tool to get to surface area. Okay, so let's set up, so this basically means that we have a set volume. So we could have like a fat cylinder like that, or we could have a little taller one, but it'll be narrower. So we have the same volume, but just a different shape, right? Or we could have a tall one that's pretty narrow. And it's just, the dimensions just depend on R and H, right? So let's start with defining some variables. So SA, we're going to let that be surface area, okay? And then we're going to let V be our volume. V is volume. R, of course, is radius. And finally, we have H, which we're going to let be our height, okay? Height. All right, so those are variables we're going to use. And let's start setting up some equations on the next slide. So let's say we have our cylinder. We have some random cylinder, okay? And we have that we want to find the surface area. So the formula for the surface area is going to consist of the area of the top, and area of the bottom, first of all. So each of those are pi r squared. So we're going to have a 2 pi r squared. Then we're going to add on the surface area of the side all around, right? So that's going to be the circumference. So 2 pi r times the height. So 2 pi r h. Okay? So this is the surface area. And now let's find an equation for the volume. So volume is given by pi r squared, so that's the base, times the height, which is h. Okay, and we also know, additionally, that the volume, the set volume we want, is 900 centimeters cubed. So this is an important relation that we have this piece right there of information, because now we can use this formula to eliminate one of the variables, okay? So what I'm going to do is get h by itself so we can eliminate that from the surface area equation at the top. So h is equal to 900 centimeters cubed over pi r squared. All right, so now what I'm going to do is take that guy and plug him into this equation here. So now surface area is going to be given by 2 pi r squared plus 2 pi r, and instead of h, we're going to plug in that 900 centimeters cubed over pi r squared. So the pi's are going to cancel out, and one of the r's are going to cancel out. So what we're left with is the surface area reads 2 pi r squared plus 1800, and then we can just kind of ignore the centimeters cubed for now. We'll ignore the units until later. So now we have this relation here where we have surface area is equal to 2 pi r squared and then plus this 1800 over r. Okay, so now that we have that equation, we can consider what is the interval for r. So what is the r interval? It's basically, it can't be negative, right? So it'll just be non-negative, so 0 up to infinity basically. It can be pretty large, okay? So there's basically no restriction on the r that we can see as of now, okay? So we'll start with working with the surface area formula on this slide. So we have surface area, which is equal to 2 pi r squared plus 18, and then 1800 over r, also known as r to the negative 1. And now what we can do is basically just take the first derivative of this. Okay, so SA prime of r is equal to 4 pi r, and then this will be a minus 1800 r to the negative 2. Okay, so this can also be rewritten as 4 pi r minus 1800 over an r squared. Okay, so now we just have to find, in order to minimize or maximize, just to optimize this function up top here, we just have to find where does its derivative equal 0 or undefined. So what we're going to do is set it equal to 0 and solve for r. So we have 4 pi r would then equal 1800 over r squared, and if we rearrange a little bit, we'll multiply by r squared on both sides, and we'll divide by 4 pi. If we divide by 4 pi, what we get is that we have an r cubed on the left side, and on the right side we get 450 over pi. Okay, and when you plug this into your calculator and you do the cube root on both sides, so cube root of that, we get that r is about equal to 5 5.23 centimeters, okay? And so since this is the only R value that we get when we optimize, we can assume that this is a minimum value, okay? So now that we have the R, we can go ahead and figure out the height. Alright, so R is about equal to 5.23 centimeters, and now in order to figure out the height, we can use the formula that we used to eliminate that variable originally from the surface area formula, which was 900 centimeters cubed over pi r squared. So now if we plug in 5.23 centimeters for this R, what we get is 900 centimeters cubed over pi times 5.23 centimeters, and then quantity squared. So this gives us about a 10.46 centimeters, okay? So this is our height here. That's our height, and the 5.23 centimeters, that is our radius. So these are the dimensions of the cylindrical can, which has a volume of 900 centimeters cubed and has the minimum surface area, which you could figure out by plugging everything in again, but the question doesn't ask for that, so we are just going to stop here. But anyways, so one other thing that I'd like to point out, it's kind of neat, is that if you'll notice, the height, which is 10.46, is actually double the radius. So h is 2 times of r. So that means that h, our height, is like r, but 2 of them in a row. So it's just as long as that. So that means that our cylinder is actually as tall as it is wide, which is kind of a cool fact, right? Lots of squares pop up in optimization. Okay, so that's all for this video on applied optimization. I hope that helps, and good luck on your homework.
This therapy for upset bitches when you with the next bitch.
No such thing as faithfully. No more winning.